So today we're going to talk about the addition of angular momentum in quantum mechanics. So we'll start out by just discussing the problem and why we might want to add angular momentum. And then we're going to move on to the example that most people begin with, which is the addition of two spin 1/2 particles, which hopefully will be very illustrative to the procedure in general. And then we'll move on to sort of more complex and more general cases dealing with this. So a quantum system may contain more than one angular momentum variable, and the two examples we'll look at most is you might have two particles with spin, and we might be curious as to what angular momentum those two particles with spin, with internal angular momentum, will combine to have. And the other real important case for us is an electron and an atom generally will have both orbital angular momentum as well as internal spin, and so we might want to look at adding those two to find the total angular momentum of the electron system. Now, these two systems are different, but the actual procedure we're going to use is the same, so that's good. So it's sort of the same idea. Any kind of angular momentum we're adding together is equivalent when we're doing this procedure here. And so just, cases where this will be important, we'll see later on in the course that there'll be some times where we'll be really interested in what the total angular momentum of the system is, not the individual. And for example, we'll find that there's cases where the orbital and the spin angular momentum are coupled. Okay, so somehow they're coupled together, and so in that case it'll be the total angular momentum that'll be conserved for the system, not the individuals. And so it'll be really important for us to be able to add up these angular momentums and understand what's going on. And then furthermore, two particles with spin can combine into a new particle with some combined spin, so that's another thing we'll be able to talk about. And so, like we said, we're going to start with two spin 1/2 electrons. And as we go through, we're going to use these operators acting on different kets. And so this can get really confusing. We're going to try to go through real nice and slow, but it's definitely important that we kind of understand the basics. Now we're going to start here with spin 1/2. Again, this will generalize to other kinds of spin, but for spin 1/2, this is basically the setup we have here. All right, and so for spin 1/2, again, this is the sort of idea here is that this is Sm. So this is the spin quantum number, and this is the m quantum number. So this tells us sort of the spin, the general spin we're talking about, and this tells us the component in we're going to do the z direction. And so we can look at when you can find s squared, which for spin 1/2 will always be 3/4 h bar squared, and then we can also use our sz operator. So these would be our sort of two key operators. So this again tells us our s quantum number. This tells us the mz, the z component of the angular momentum. And again, for our spin 1/2, the simplest case, it's either spin up h bar over 2 or spin down. And then the final thing that we'll use, we'll need to use sometimes, are the raising and lowering operators. And just be real careful. So we're going to talk about this a lot, but really the key thing here, or one key thing, is just getting through all the different ways you can write this. And so again, in a sort of real slow sort of case, this is Sm, right, for our procedure here, but a lot of times we'll use the shorthand here of either the spin up arrow or the spin down arrow. So this is kind of the support of all the information out there, but at times this will be a little bit of overkill, right? And so all we really need would be these sort of spin up and spin down parts. I just wanted to talk, again, kind of slow down and sort of just think about this. So if we have just one spin 1/2 particle, what is the Hilbert space dimension? Well, it's going to be dimension of 2. And what are the possible values of s? It's always going to be 1/2 for this guy. And what are the possible values of the m quantum number? It's 1/2 and -1/2. And so our dimension is 2, which means we can represent any ket as a linear combination of spin up and spin down. And that's what we get the d = 2 dimension for that there. So our first step is going to be trying to represent what we call the composite state, and this is where you're looking at the two individual particles separately. So for each one of our spin particles, right, we're going to, to specify the total state, we need two quantum numbers, the spin quantum number and then the m, so the s and the m. And so basically here we have the ones for particle 1 and the ones for particle 2. And so your most basic way to represent your composite state, so basically these two states together, would be writing it out like this, two separate kets. And I see a lot of people will sort of write out here where it's just one ket, Again, this is going to be a problem in that basically everybody represents this a little bit differently. I'm not sure why it is, but usually, hopefully, they'll have some part in there where they're sort of clear as to what they're doing. And so for our spin particles, for instance, here we could have this be our spin particles. And so generally we have sort of a particle 1 and a particle 2. So particle 1 has an s of 1/2 and an m of 1/2, and particle 2 has an s of 1/2 and a m of negative 1/2. And so we can write it that way. You also see people write it this way here, which can be really confusing because then you have these sort of 4 numbers and you're not sure which is which. And there's actually people who will sort of switch the order of these. Again, hopefully they're clear. We're going to try to be super clear. But also, hopefully you see that in this case, these first 1/2s are kind of redundant. We're dealing with spin 1/2s. We know the s quantum number is going to be 1/2 for both of them. And so what we're going to prefer to do is write it this way. And so this is basically saying that particle 1 is spin up and particle 2 is spin down. And we call this the composite state, or at least that's what Griffiths calls it. So that's what we're going to call it too. And so this is the way to represent the composite state. And so you'll see that for 2 spin 1/2 particles, there'll be 4 composite states, and basically just the different kinds of arrangements we can have with these spins. You know, the spins can either spin up or spin down, and so if you're treating them as 2 separate spin states, there's basically 4 ways you can write it out. And again, you can sometimes see it written this way. We'll prefer to write it this way, but hopefully you can see that it has the same information in there as long as you're clear about what those numbers represent. And so let's move here. And so what we're going to do now is we're going to represent, or we're going to start having 2 separate kinds of spin operators. Basically one that's defined for particle 1 and one that's defined for particle 2. And the way that it works is the spin for particle 1 only operates on the information for the spin particle 1, and the spin of 2 only operates on the one for number 2. And so this is probably one of the most confusing parts when you're starting out with this, and so I thought we'd start here with an example. And so here I want you guys to think about what would be the result of the operation SZ2. So again, that's the SZ operator acting on particle 2 on our ket over here, spin up, spin down. So go ahead and pause this and think about this for a second, and we'll talk about it. Okay, and so hopefully you got D for this one. Let's go through this and do this explicitly. Now, the way I like to sort of talk about it now when we're just starting out is you can kind of take this, and it can be convenient, especially, you know, when you're starting out, just to sort of write these, you know, break them up like we've been doing into the 2 different states. And what happens is this operator, when it's acting on the second particle, it only operates on the second particle. And so it doesn't affect this guy at all. So you can slide these around, and so you can do something kind of like this here. So you can take the SZ of particle 2 inside over here. And of course we know how this operates, right? So this will give us back just the eigenvalue, which for this it's the spin down. So it's negative h bar over 2 spin down for that second particle. And again, this is just a constant. I can pull that out front, sort of like this here. And then of course, if you want to give it right back exactly to the nomenclature we were using before, you would kind of go like this here. Of course, oops, sorry about that, there's a typo there. And so that's how to do that. So we're going to do some calculations as we go along with these different spin operators. I will note that there's a more elegant way to do this, dealing with what's called the direct product. I don't know of any first-year quantum mechanics books that really go into this. Just so you're aware, some people might mention this, but I think most people kind of try to do this the way we're looking at it here. All right, so here is sort of a summary then of these new operators, which are just the old operators, but now again there's one that only acts on particle 1 and one that only acts on particle 2. And so this is the s squared operator for particle 1, so it gives us back information about particle 1. S squared for particle 2, same thing, gives us back the S2 information, and we have the same 2 for the Z particles. And so we can use these and try to get a feel now for sort of what's going on with these composite particle states. Now, our goal here is to start with these composite states like we've done, and what we want to learn about is what's called the combined state. And so you can think about this as when you add 2 kinds of angular momentum, right? The result is going to be some state that you can think of as almost like a new particle with a new angular momentum. And so basically when the combined state is set up, we can think about what its S quantum number is and what its M quantum number. And these will generally be different from the 4 individual ones. And so that's going to be our goal. And again, we're going to do this using the 2 spin 1/2 particles. And so we're going to discuss how this works in practice. And so what is the total angular momentum? Well, the total angular momentum, these are boldface, so these are all like vectors, is the total angular momentum is the first angular momentum for particle 1 plus the particle angular momentum for particle 2. Now this can be pretty nasty in practice to figure this out. And so what we'll generally do is start out with the SZ, right? Especially when you consider our sort of operator of interest is S squared. So squaring this is not going to be pleasant. So we're going to put that off as long as we can, but we can start with the total SZ operator, which is going to be SZ of particle 1 plus SZ of particle 2. And so if we apply that, so here we're applying the total SZ operator on our composite system. And what we get, similar to what we did before, is you get basically you get the M1 H bar for the first particle, particle 1, plus M2 H bar for the second particle. So we're looking at these two particles, and we're basically saying what's the total Z component for these two particles in the particular state that we're talking about. And so when you're done, you simply get just M1 plus M2 H bar. And so what does that mean for us? Well, if I apply this total SZ operator on our spin up composite state, I'm going to get just H bar. So the 2 1/2s add up and give me 1 times H bar. If I apply this on the 2 down states, I'm going to get negative H bar. And then the sort of in-betweens, if I apply this total SC operator on one where it's in between, I'm going to end up with 0 as the quantum number. So again, it's basically just 1/2 plus 1/2, or negative 1/2 plus negative 1/2, or some sort of mixed up version of these. And so that means if we look at our 4 composite states, if I look at just my MZ quantum number, so for this case here, I'm going to get 1 when they're both spin up is 1/2 plus 1/2. Here I'm going to get 0. Here I'm going to get 0, and here I'm going to get negative 1. So we start by sort of looking at the Z components, which are going to be a little bit easier for us to untangle. So let's just stop a little bit and think about when you're adding 2 angular momentums. Now if you think about, classically, so suppose we just had 2 vectors that you were going to be adding. Well, we'll call them S1 and S2. Well, if you think about it, the maximum you could have is if S1 and S2 are in the same direction. So the max would be S1 plus S2. And then you would think the minimum would be when they're sort of added up in different directions like that. So again, this could be anything, S1 minus S2. And so that's the way it actually works in quantum mechanics. And so if we add spins S1 and S2, what total spin do you get? Well, basically you get every spin from S1 plus S2 down to S1 minus S2 going by integer steps. And so for instance, in this case, we've got S1 is 1/2 and S2 is 1/2. And so if we add them up, okay, we get an S total of 1. If we subtract them, we get an S total of 0. Now, you could have anything in between by integer steps, so that's where the quantum mechanics comes in, right? So classically, if we're adding up 2 vectors of 1/2 like this, our max would be 1, our minimum would be 0, and we could have anywhere in between. Well, you can't have anywhere in between in quantum mechanics. You can go up by integers of 1, which would be 1. And so in this case, it's just 0 and 1. So these are our total spin states. Now, let's think about this. Okay, we know that our spin states have 2s plus 1 different states. And so that means, which is, different levels of m. And so for s equals to 0, you have m of just 0. For s equals to 1, right, you can have m going like this. So again, that goes from negative 1 up to 1, going in values of 1. So negative 1, 0, and 1. And of course, over here, 2s plus 1, that tells you how many states there are for s equals to 1, if I plug a 1 into here, I get 2 plus 1, I get 3. So 3 states, these are the 3 states over here. For s equals to 0, I get just one state. This is the one state over here. And so either way you represent this, you're going to end up with those same 4 states like we were talking about. So the composite states, there's 4 of them. Now here, there's going to be 4 states when we write it combined. It's just they're going to be organized separately, but it's still the same number of states. And so what we do then is we look at our states here, and so we're going to want to try to build those combined states in terms of the composite states. And so what are we actually talking about here? Well, if we had these states, we would represent them, again, the sort of nomenclature is SM, where these are the total. And so here it would be like 1, 1, 1, 0, and 1, negative 1. And then this guy would be 0, 0. And so we want to somehow represent these states in terms of our composite ones. And so if you look here, hopefully you can see that mz equals to 1. This has to be the state 1, 1. It's the only one that has an mz of 1, and so it's sort of the only possibility. So we can say that 1, 1 is just going to be spin up, spin up. By similar reasoning, we can say that our state negative 1 is going to end up being this guy over here. And so right away we can sort of say, well, here's one way, or at least here's 2 relationships we have between our combined states and our composite states. And again, just one last time, composite is treating them as 2 separate, spin up and spin up. And here it's treating them as some sort of combined thing where it's like a new, you can think about it as being like a new particle. And so when they're both spin up, it's like a new particle that has spin 1. And its mz component would be 1 in that particular case here. Here's the option where your combined states give you a total spin of 1, but the z component is in the negative 1 direction. Now, the in-between states are a little bit more complicated, and so we'll talk about those, but hopefully we're getting somewhere. So now what we're going to do is we're going to use our raising operator to try to find what the next state is. So we've sort of argued that we can say that the spin down should be S1 M negative 1. And so what I'm going to do is I'm going to define our total S plus operator, so the raising operator, as S plus acting on the first particle plus S2 working on the second particle. And so I'm going to apply this on this state we just wrote out here. 1, negative 1. And so on this case here, we can go to our definition of our operators. And so S plus acting on 1, negative 1, what it does is it steps up to the next rung, which would be m of 0, and gives us a coefficient. And the coefficient is this ugly thing here. So we can write that in. So it's S plus 1, negative m plus 1, where those s's with s is 1 and m is negative 1. Now if you take this and plug in the appropriate values into this, right over into here, I would get h bar. Then here you get 1 plus 1, or 2 times 1, minus, and so this is minus 1, and here it's minus 1 plus 1, which hopefully gives us 0. And so I end up with h bar times radical 2 times 1, 0. And so that's just knowing how this operates on some general SM state. And so now we apply these 2 guys onto this thing. And so the way I would write that out carefully is I'd say S plus for the 1 particle, number 1, and S plus for particle number 2, and that would be times these 2 states. And so what would happen is I would just distribute this. So this would be times down, down, and then plus S plus 2. And we described how these operate on spin 1/2. And so basically it's going to raise the state. So this one's going to raise the first one. And so I'm going to have a state up, down. And the coefficient in this case, which is again is using the same thing here, but we talked about it already for spin 1/2, we just get h bar. And so this steps up this guy to h bar, and then over here this is going to step up particle 2, and so it'll be down, up, like so, with again another factor of h bar. And so we can go through then and clean this up a little bit and get a state such as this here. And so what's really nice is I can sort of divide both sides by the h bar and get rid of that, and I can write 1, 0 is equal to, and if we divide by this factor over here, 1 over radical 2, and we get this linear combination of these two states here, like so. Now if you recall, so we knew that these states here have m of 0, right? But we were trying to find the one that's got s equal to 1. And so the way we did that is by actually stepping up, using our raising operator to actually find that state explicitly. Now I will say that this is the kind of thing we're going to do sort of a couple times, hopefully to help with our understanding, and we'll see that there's sort of faster ways to do this. But hopefully you can see how this is pretty powerful. So now we've found the other, or one of the other combined states that we wanted. Now, I just wanted to kind of talk about the broad strokes of this. So technically what you'd want to do now, right, is show that if I apply the S2, where this is the total spin squared operator on this thing, right, what do we get? Well, we get back S plus 1 times h bar squared, excuse me, times 1, 0, which in our case here for spin 1 will just give us 2 h bar squared times 1, 0. Now what we'd want to show is that this s squared operating on this second guy over here gives us that same quantum number. It's going to give us 2 h bar squared times this. The textbook runs through this. I'll probably do this in a different video, but it's kind of a beast. And why is it a beast? Well, it's because you're doing s squared of this thing. So again, this is like the spin vector 1 plus the spin vector 2. You're taking that and you're essentially dotting it with the same thing twice. And so this is kind of beastly. It ends up, being very, very, a lot of algebra. So it's not too pleasant to do this, but it is something you kind of probably want to run through and do a couple of times. And so when I do this, S1 dotted with S1, so I'd have S1 dotted with S1, and then I'd have the S2 vector dotted with S2, and then I'd have the two cross terms, if you will. So S1 dotted with S2, these are all vectors, plus S2 dotted with S1. Now, one thing we'll note, we didn't really mention this yet, but the spin operators of S1 and S2 commute. So we can move them back and forth, no problem. And so over here, S1 and S2 dotted with each other are the same thing. So we can sort of boil this down. So here, this is just going to be our S1 squared plus S2 squared, right? Taking that dot product is just going to be the same result as doing that. And then this will be plus 2 times S1 vector dotted with our S2 vector. And of course I could have done it the other way, it doesn't really matter, but this is how we will traditionally write this out. This last piece is the one that's kind of nasty, because we know how our s squared operators will act on these guys over here. So this last piece, you can write it a couple different ways. Technically to write out this this guy here, right, if I was to sort of just write out this piece, it would be a factor of 2 times sx1 sx2 plus sy1 sy2 plus sz1 sz2. So this is what like I said, it's good to go through and just kind of convince yourself that this raising and lowering operator business that we did worked. And so I'll probably do that in a different video. The book also goes through that. But basically we end up with this statement here talking about the combined states. And this is really important. We're going to use this literally for like the rest of the semester. And so it's something we really want to go through, but we can express our composite states in terms of the combined states, where again we're looking at this as sort of two particles coming together to make another particle, if you will. And so there's what we call the triplet, which is the s equals 1 states, and that's literally just triplet because there's 3 states, and it's the singlet. So this is so important, we've given them their own sort of funny name, which is the s equals to 0 state. Now this one we didn't derive yet. This one basically you go through, and what you realize is that this state over here, I want this state to be orthogonal to all these 3 guys. And the easiest way to do that, or the way we're going to do that, is by expressing it out this way right here. Okay, and so that's something else we'll probably do like in a separate video, where basically this has the positive sign, this has the negative sign. Of course, this positive sign and this negative sign are super important. We'll have lots to talk about with this difference in signs, but for right now, it's just the way we represent our combined states. And so we can sort of think about these as the composite or the combined. This again was our example for adding a spin 1/2 and another spin 1/2, and in class and later we'll talk about the more general procedure, but this is the one that we generally start with, and again, it's probably the most important one.